Hey you guys, well here I am sitting in my office thinking about making videos for you that go along with the PowerPoint slides that accompany this class. I have posted those PowerPoint slides on your D2L shell for you to look at, and I'm going to annotate these a little bit and talk through them, help you with your fun sheet for when you turn that in. Chapter 8 is all about the periodic relationships among the elements. This is kind of piggybacking off of Chapter 7. We learned about electrons and electron configurations and how those electron configurations repeated in different columns of the periodic table and then gave those columns similar reactivities. So now we're going to see that really closely in this chapter and look a little bit more at those electron configurations to see how they are periodic. So let's start. This is quite somewhat of an historical chapter in the fact that it goes through the different elements and when they were discovered, and so I'll let you guys read that history about that. And of course, ancient times you'll see things like copper, silver, and gold were common. Lead and tin, even the Romans, used lead to make vessels. Iron, then of course we had the Iron Age, but then up through all the different years, then we ended up with kind of now where we are with creating our own elements in cyclotrons and so on. So don't worry about that too much. This is just a bit of a history of when elements were discovered. Now the periodic table was built by looking at how the elements behaved. John Newlands was one of the first people to start looking at this, and he arranged elements in order of atomic mass. So as the elements got heavier, it did make sense that, to put them from low to high, and that's what he did. And he found that every eighth element had similar properties and called that the law of octaves. You might have heard of that as the octet rule. But it didn't work beyond the element calcium, and that's because the d orbitals showed up, which could hold 10 electrons, if you remember from Chapter 7. Dimitri Mendeleev was another scientist who grouped elements together more accurately according to their properties, given that alkali metals went with alkali metals, halogens went with halogens, and so on. This made possible the prediction of elements that not yet discovered. There were a few elements, holes in the periodic table that weren't discovered till much later due to this grouping by similar properties. Henry Mosley was another one of our scientists. Now, he was active during World War II. He actually died during World War II, and that was kind of sad because he found that the relationship between the atomic number and how to order that in the periodic table. So Henry Mosley determined the atomic number of many elements by bombarding that element with high energy electrons. If you remember Rutherford's experiment, he was bombarding gold foil with alpha particles and then seeing how those alpha particles were deflected or bounced back, and that gave us evidence for the nucleus of the atom. So anyway, Mr. Mosley determined the atomic number by kind of doing the same thing, but then I have two graphs here that show the relationship between the X-ray frequency and the atomic number and X-ray frequency and atomic mass. So the relationship that he determined by taking these measurements is given in this formula right down here. This is that's the frequency of the emitted radiation of the the foil. So what was interesting is that here, if you think of a piece of foil, he bombarded the X-rays through the foil of the different elements, and then there was a relationship between the atomic number Z and the frequency that was emitted from the element. So it looks like what's kind of funny is that you see this relationship over here and think, wow, that's pretty good straight line, and it is. And that's atomic mass versus that square root of the frequency of the X-rays. But this one's like a rock solid one. It's very, very close to perfect. So you can look at the periodic table and find some anomalies where atomic mass goes down from one to the next, and that occurs. You'll see that occur in iodine, from tellurium to iodine. And actually, its atomic mass goes down just slightly, though. Then that's why this is this one over here is pretty good, but this one is even better over here. So anyway, that's what Mr. Mosley did. He was 26 years old when he determined that relationship. So further on classifying the elements are classified according to representative elements, which are in this gray area, which are the S and the P's. Then we have the noble gases. The noble gases are the helium down through radon. The transition elements are in this middle section. Then cadmium, zinc, and mercury, they're kind of in their own little category, and that's because the definition of a transition metal is that does not have a filled shell. So zinc, cadmium, mercury are completely filled, and that's why they don't fit into that category. The lanthanides are down here, and the actinides are here. Lanthanides start with lanthanum. Actinides start with actinium, and that's why they're called that. Now here we are kind of back into chapter 7. Remember that there were noble gas configurations for all of them as the core electrons. But what this is showing is the ground state outermost electron configuration for each one. So in this one, NS1 is the outermost electron configuration for everybody, N being that principal quantum number 1, 2, 3, or 4. The alkaline earth metals, NS2. The alkaline, sorry, I'm stuck on alkaline there. Trying to draw my S. The noble gases over here with a filled shell, that would be NS2NP6. And then we have our halogens, which are right here, and they're NS2NP5, and so on. So if you analyze these electron configurations, it can kind of give you some insight into the ions that form for those individual elements. The alkali metals over here are NS1. Like to form that positive 1 charge when they come and get into chemical combination. The alkaline earth metals, NS2, and that means that they form positive 2 ions when they go into chemical combination. The transition metals kind of do sometimes remember different things. Iron, for example, can be iron 2 or iron 3. So if he's iron 2, that means he loses 2 of his electrons. If he's iron 3, he loses 3. They're both stable cations of iron, and you'll find them in different minerals and so on. So this slide is just giving you an idea, and this is a figure out of your textbook that gives you a picture of the electron configuration for the elements and how those electron configurations feed into the formation of the ions. And there you go. It's going to show you that again, NS2, and all those different outermost electron configurations for each column. And those, remember, those are called families. And then we're going into the, even a little bit into the transition metals. So when you have a chance to work on fun sheet 1, the goal for fun sheet number 1 was to just get you filling in the periodic table and get a feel for all the different parts of it. So when you're finished with that, shoot yourself a picture and submit that to the discussion board. Now, looking at what I was talking about earlier about the electron configurations of cations and anions of representative elements, remember representative elements are those A groups. So when sodium, for example, forms a cation, it loses its 3s1 electron, which makes sense. When calcium becomes positively 2 charged, it loses both of its s electrons. Aluminum becomes positively 3 charged and loses all of those electrons on the outermost shell. These are valence electrons. Valence electrons are the outermost electrons outside of the core. Remember, the core is this noble gas. Hydrogen, what can hydrogen do? Hydrogen can do actually both things. I'm surprised it's only listed here. Sometimes if it gains one, then it will become hydride and it looks like helium. But hydrogen very commonly can be positive 1 as well. But he's not positive when he becomes an ionic compound. This is an ionic compound, something like sodium hydride. You would see something like that. Over here, when hydrogen is taking this positive role, something more in a covalent compound like hydrogen chloride that you're familiar with. Fluorine likes to become fluoride, gains an electron, pops right into that P shell. And oxygen likes to become oxide and gains 2 electrons. Notice they are becoming neon. This means they are isoelectronic with each other, meaning same number of electrons. So fluoride and oxide are isoelectronic. That's a terminology meaning the same number of electrons. Nitride would also be isoelectronic with these other. So all of these are isoelectronic. They all have 10 electrons, these ions. So I feel like we've already been here, cations and anions of the representative elements, but again, this is just showing why. On the previous slide, we were looking at this alkali metal where NS1, and that meant it lost 1 electron to become that positively 1 charged stable cation. So again, look at these charges, +1, +2. Now we know why it forms those charges. And sometimes people ask, why didn't we learn this before? And it's because we are studying chemistry in the order that it was discovered, not kind of now that we know. And sometimes it's nicer to do it now that we know. But sometimes when we jump into first thing atomic and molecular theory, as far as like quantum theory, people get a little freaked out. So sometimes it's nice to be able to do this first and all those substances, elements, and then come back to this. So here we are. Let's do a little bit of practicing. If we now know something about the electron configurations of each element, if I give you a hint of something has 20 electrons, what would be the ground state electron configuration? Well, we just start at the bottom like we did in chapter 7. 1s2, 2s2, 2p6, 3s2, right? I mean, how many electrons am I at this point? Did I already add too many? Let's count. That is 10. Nope, that's 12. I feel like I should do more. 3p6 and then 4s2. So if you add all those up, you get 2, 4, 10, 12, 14. Wait, no, I added wrong. 2, 4, 10, 12, 14 plus 6 equals 20. So that equals the 20 electrons. And I didn't even know who it is, but who is it? Classify. It is an alkaline earth metal. It's calcium. Ca. Paramagnetic or diamagnetic? If something is paramagnetic, that means all its electrons are paired. And sure enough, if I did draw the orbital diagram, everything is paired. And this would be argon. All electrons are paired, so it would be diamagnetic. So at this point in chapter 8, we're kind of looking at a descriptive view of the elements and the periodic table. So we're just like you say, if I start drawing something like this, and this is going to be really hard for me, I would draw this on the board. Remember how I have my favorite animal? If I start drawing this, you might say that looks like a horse. Yes, it is. So just like if I started drawing that electron configuration like I did above there, this is calcium. And if it's diamagnetic, it means all its electrons are paired. All right, I'm going to finish that up. All right, let's move on. Isoelectronic, I mentioned earlier, it means everything, if you are comparing two atoms, whether they're ions or neutral atoms, if they have the same number of electrons and the same ground state electron configuration, they are isoelectronic. All of these are isoelectronic. They all have neon as their ground state electron configuration. All of these are isoelectronic. So here's a little game. What neutral atom is isoelectronic with hydride? Hydride is 1s2. Well, who is 1s2? I'm going for helium. And there it is, helium. So when you get a chance, work fun sheet number 2 and put that on the discussion board. I give you an example here to write chemical reactions. You think at this point in chemistry, wow, now we know how to write chemical reactions because we know what things are made of, and we also know how to write things that are in their elemental state. Things like there's diatomic elements like oxygen, nitrogen, all the noble gases, all the halogens travel diatomically. You have things that travel monoatomically, such as the noble gases. Do we see a noble gas here? Yes, we do. Noble gas, it would make xenon tetrafluoride. So don't put these labels on things. And this one would be, it's neutral. This would be a gas. It's neutral. And then it would form magnesium oxide. Now, you have to remember that magnesium likes to lose 2 electrons. Oxygen likes to gain 2. So it's a 1-to-1 relationship. And magnesium oxide is a solid. And if we balance it, we can just put a 1/2 right there. And it's balanced. So when you get a chance, go through and do the same thing. Keeping in mind how the elements travel. Are they diatomic? Are they monoatomic? Or whatever. And also what the phase label should be for that specific element. Or that compound, like carbon dioxide. What phase label goes on carbon dioxide at room temperature and pressure? Or sodium chloride at room temperature and pressure? So let's do a review of concepts. That's on around page 333 in your textbook. What would be an alkaline earth metal ion that is isoelectronic with krypton? Well, krypton has how many electrons? If it has 36, then we have to go to the alkaline earth. Who are the alkaline earth metals? They are column 2. So it's an ion as well. So that means it's gained or lost electrons. But now if it's a metal, metals like to become positive. Since they become positive, that means it will have lost electrons to become 36. So who must that be? I'm thinking it's Sr. Sr, if he loses 2 electrons, then he will have the, oh, I already messed it up. No, I didn't. It looks funny. I'm looking at my periodic table. Make sure you're looking at your periodic table. I'm still thinking it's Sr. Sr, and I can check myself by knowing that Sr is number 38 when he's neutral. If he loses 2 electrons, he becomes 36. Okay, let's try this one. If it's an anion, that means it's negative, and it's isoelectronic with potassium positive. So potassium normally has 19 electrons. If it becomes positive, it now has 18 electrons. So what anion that's negatively 3 charged, and this is going to be isoelectronic with argon, will have 18 electrons? 18 minus 3 equals 15. Who's number 15? It's phosphorus. So phosphorus, after he's gained his 3, becomes phosphide. And now that it's phosphide, it is isoelectronic with argon, which is isoelectronic with potassium plus 1. Okay, how about an ion with a positive 2 charge? It's isoelectronic with cobalt 3 plus. Find cobalt on your periodic table. It is number 27. Since it's number 27 and cobalt 3 plus, his number of electrons at this point would be 24. So whatever I'm searching for has 24 electrons. Now it was positive 2. So I'm thinking that it must have been number 26. Who's number 26? Number 26 is iron. So iron metal becomes iron 2 plus. And when he becomes iron 2 plus, he had 26 electrons. Now he has 24, and that is isoelectronic with cobalt 3 plus. Remember, this is an oxidation half reaction. Okay, looks good. Now keep on going with electron configurations, and now we're in with transition metals. Transition metals tend to do a little bit different. Most of the time we were losing S electrons. Now, and we still lose S electrons, but sometimes we lose D electrons. For example, iron. First he loses his S's to become iron 2 plus, but then he's got to lose a D to become iron 3 plus. And this is a very happy configuration because you'll read later, or you might have seen in chapter 7, that half-filled orbitals are stable. Half-filled and completely filled. Here's manganese. Manganese, to become its charged, 2+ loses its s electrons. So this is a little fun game to play. Which element am I? We all have 3+ charges. Well, if it's this now and it's 3+, that means it's lost 3 electrons. So who is argon? 3d6. And actually, argon is 18 electrons. 18 plus 3 is 21, plus another 3 is 24. I'm sorry. Yeah, I got that, 24. Who's number 24? Chromium. See if we got it right. We did. Chromium's under there. Sorry for writing over that. How about this one? Scandium. So it looks like we just have to add 3 every time and then see who that is. So this looks like 45. Rhodium. And that should be iridium, number 77. So anyway, this is just a way to realize that when you get these electron configurations of ions, you got to think about how that ion either lost or gained electron. Now we're going to keep talking about the kind of descriptive, remember, description of the periodic table. One of the descriptors of an atom is effective nuclear charge. The effective nuclear charge is this positive charge felt by an electron. So that must be coming from the nucleus. But what's kind of weird is that we end up, since, remember, think about an atom like this, you know, even though we don't love to draw that. There's a nucleus in the middle. And if you have electrons way out here, they are not feeling as much pull as the electrons that are closer. So that effective nuclear charge is the charge felt by the electron. So this little shielding thing here, this shielding constant depends upon how far away the electron is. And this number of inner or core electrons, Z effective, is Z minus the number of inner or core electrons. So let's see an application of this. Here's sodium. Here, this is the atomic number of all of these elements, 11, 12, 13, and 14. The core for sodium is going to be neon. The core for magnesium is neon. The core for aluminum is neon. I think they're all the same. So now we have 10. But you see the effective nuclear charge felt is different. This guy feels 1, 1, 1, 1. Just one effective nuclear charge, whereas this one feels 4. What does that mean? It looks like since this one is feeling a higher effective nuclear charge, it is smaller in size. So that's why on the periodic table, as you travel from left to right, which is what sodium, magnesium, aluminum, and silicon were doing, you get a small, your size gets smaller because your number of protons is increasing in the nucleus, and then those electrons are feeling more of a pull, so they're getting sucked in. So if you feel like here's your nucleus and then you have these shells out here, the electrons out here, and you'll notice these that we were studying were all in the same row, and that meant we never went out further than 3, 1, 2, and 3. And that meant we were adding electrons. And we were also adding protons. And the more protons you add, the more pull these feel, and that's why it gets smaller. So effective nuclear charge has a trend from left to right, and we'll see that in a second. Well, I'll let you guys play with this. I'm not going to give you all the answers to this one. We've done some examples like this already. So I'll let you guys go ahead and do that. Now, effective nuclear charge, we were just talking about this. And as we were talking about it, I said there was a trend. And as you move from left to right, you have an increasing effective nuclear charge. So your atom got smaller. I mean, it doesn't get much smaller, but it does get smaller as you go from left to right. Now, atomic radius is defined as half the distance between two nuclei and two adjacent what? I don't know if I'm going to get any fill-ins for this. Metal atoms are in a diatomic molecule. Because you think, well, what does this mean? This is just a definition of size. So the size of the atom is this plus this, which makes the whole. Or if it's a gaseous molecule, it's this plus this to make the whole. So there's covalent versus metallic is how you're seeing the difference of those. Now, we just covered effective nuclear charge, and this is a slightly different way of looking at it. But as you go from left to right, you'll notice it's getting smaller and smaller. And as you go from top to bottom, it gets bigger, or from bottom to top, whoa, it gets smaller. So it does make sense that you have more shells for these ones down at the bottom versus as you go up. So of course the electrons are further out down here and it's a larger size. This is one of the favorite questions on the final exam. How, they give you some different ones. They say, who's bigger, phosphorus or chlorine? And you would say phosphorus because of the trend. Or who's bigger, iodine or chlorine? It's iodine because iodine is further down. So those are some, do you really understand the topography of the periodic table is what that's asking. I'll let you try this one on your fun sheet. You were to draw these arrows in, and by drawing these arrows in, hopefully you'll recall what those trends are, so when you take your exam, you'll be okay with that. Your book likes to give us some kind of neat graphs here that show us the trend in atomic radius as you go from left. Lithium is on the left side, fluorine is on the right. So as you go from left to right, you see a decrease in size. Now you'll see some strange anomalies throughout here, and that's because you end up going into the transition metals, going the lanthanides and the actinides. So these trends work really well in the representative elements. So if we had to arrange the following in order of a decreasing atomic radius, it looks like we're in sodium, aluminum, phosphorus, chlorine, and magnesium. These are all in the same. These are all in the same. You have a decrease as you go from left to right. So put those in order of left to right, and then you'll see that decrease. Again, to arrange different, looking at the periodic table, phosphorus, silicon, and nitrogen, that would be the order. And then if you had to compare the size of some pairs of atoms, you would do the same thing, beryllium and barium. Beryllium is number 4, barium is way below at number 56. So barium would be huge compared to beryllium, so you can practice those. Now what about isotopes? Are isotopes different in size, or are they just different in their number of neutrons? Remember, neutrons are what are different there, not protons. So neutrons do not have effect on the size of the atom. They have effect on the mass, but not on the size. Now, as far as ions are concerned, when ions are formed, an atom either gains electrons or loses electrons. If it loses electrons, it gets smaller, hence the smaller. If it gains electrons, it gets bigger, hence the bigger. So when a chemical reaction occurs, like to make lithium fluoride, which is an ionic compound, lithium gets smaller and fluoride gets bigger. The cation is always smaller and the anion is always larger than the atom from which it was formed. So your book gives you a nice little graph here. Now there are some trends here, but these trends stop right here because these are anions on this side and these are cations on this side. So you do see a trend, kind of similarly, that as you go from top to bottom, it gets larger for the same reasons. And as you go from left to right, it gets smaller for the same reasons. But as soon as you go into gaining of electrons and making anions, now it's going to get much larger. But you do see from the cation to the anion, but you do see a general decrease in size right here or right here. So doing some practice, which one is going to be larger? You have to check out their number of protons and their number of electrons. Nitrogen has 7, fluoride has 9, well, fluorine. But then when they become their anions, nitride and fluoride, they have the same number of electrons, but nitrogen, let's check it here, nitrogen has 7 protons and 10 electrons. Fluoride has 9 protons and 10 electrons, and that means that these are going to pull these much tighter. This is only 7 protons, not enough to pull those in. So this guy, fluoride, will be smaller. This guy will be larger. Okay, so for magnesium and calcium, same analysis. Calcium is going to be larger. Let's check out why. It's asking on which species is larger. Why is calcium larger? That's a good question. Then magnesium. Well, magnesium has 12 protons. Calcium has 20 protons. Magnesium 2+ has 10 electrons. Calcium 2+ has 18 electrons. Now, the question is which one's larger? It's almost a no-brainer because calcium on the periodic table is lower than magnesium. It goes magnesium and then it goes calcium. So as you go down, you're going to add another shell, and so of course it's going to be larger no matter whether it's an ion or not. Iron 2+ or 3+? I think whichever ones, I think iron 2+ is going to be larger because once you lose another electron, you're going to have a higher attraction from the nucleus. So iron 2+ is larger. So now try fun sheet number 6. This gives you an idea of how to do that. Now this one's mixing up anions and cations. So you got to think about that. And you can always go back to that one picture in your textbook.